It's all of these points on this side of the line, right, with taking those out. That's your domain sketched in two-dimensional space. Okay? Yes?
Would it create an asymptote at that point?
We don't know what's going to happen. When you say that point, do you mean this vertical line? Yeah, we're not quite sure what's going to happen, right? We have to look at, the function will dictate that. In this particular case, yes.
Yeah, that's what I mean.
Yes, because we'll get division by 0 when the numerator is not going to 0. So we'll have some sort of asymptotic behavior. We're going to look at the graph in just a moment.
You can't go to negative infinity either, because that would be below our line.
Well, yeah, let's go to part E. Determine the range. Now, determining ranges of functions is normally much harder to do.
Yeah.
A range for a function is, unless the function is simple, it's pretty hard to determine ranges. But I think we can do it here. Do we all agree that the numerator is always positive, no matter what, right? And the denominator could be positive or negative depending on my value of x. So it seems reasonable to think that I probably can get out almost every positive number and every negative number that I could think of. Now, on the notes I put here, determine the range. I'm never going to ask you to determine a range on a test or anything like that, because it's just not simple. Instead, what I want you to get used to is going to some software and graphing this, using the software. So I used GeoGebra again, right? And let me erase all this. Do y'all see what I typed in right here?
Yep.
Z equals, and then I typed in the function, and I'm about to have it graph for us, all right? And this is what it graphs, all right? And I'll spin it around because that's kind of a cool feature. That's the graph of that function of two variables. It does. Now I'm going to go back to my notes. I'm going to go back to my notes because I think my graph is better than that actually. Okay, this is the graph. Mine, Mathematica's graph, is better than that one because you can see the asymptotic behavior there. Do you see that? And watch, if I look at this from the top, well, I have top view right there. If I look at it just from the top, straight down, right? That's like we're way up at infinity and we're looking straight down. Do you all see the domain? Mm-hmm. That's the domain of the surface. I mean, you can see it, right? That's a domain. That's everything shaded on that side of the line. Take out that x equals 3. But that's actually the surface, right? At every point, if I rotate this up, like every point is plotted, right? That's all the different points that you can plug in, plot it, and you create this surface. Now, this kind of weird taper effect here is just the computer giving up because it's an asymptote. Okay, let's look at our next one. These look like surfaces, don't they? They're surfaces. That's what we're looking at, a surface. Something kind of floating in the air. It's like we have the domain on the ground, and then we have some sort of like sheet or some sort of surface floating above it. As you write that down, I want to go back because I skipped over a note. I'm just kind of assuming that we all understand this, but I want to show it just in case. The whole idea of a function of two variables is that if you give me an x and a y, I should be able to plot the z value, right? And if I do that for all the points in the domain, right? If I have a bunch of points that I start plotting, right? I start plotting out just a few more. I start plotting all of them, right? Then I'm going to create this surface, right? That's what I'm going to get, is some sort of surface eventually, if I can imagine all those points together. That's what we're doing. And if we look at just the whole surface, this is just an animation where you can actually say, go pick a point in the domain, and then over here it shows that point being plugged into the function. So the z value is the value of the function if given that x and y input. There's your z. Your z is the height of the point. So as I change my x and y, right, move around, I'm at a different point on the surface, right? At every point over here in two-dimensional space, I'm on some other point on the surface over there. Okay, that's what we're doing here. All right, there's our next one. All right, did you all try and plug in 3,2 already? So f of 3,2 is, let's see, 3 for x, natural log y squared, 2 squared minus 3. So equals 3 natural log of 1, but natural log of 1 is 0, so that's just 0. All right, that's just 0. 3 goes in for x, 2 goes in for y, 0 comes out for z. So if I go out 3, then 2, I'm just going to stay there. Not going up or down, right? 3, 2, stay. All right, what's the domain of this function? So look at this function. X by itself is no problem, right? You can plug in any value you want for x. But we do have some problems with logs. When it comes to logs, we cannot have, or we have to have positives. Can't put negatives into logs, can't put 0 into log, right? So in terms of domain, the one thing I have to worry about here is that the argument of that log function, right, the thing inside that log function, has to be a positive number. And this is a quadratic inequality, right? So the way I'm going to solve this is almost the same way I just did that other one. I'm going to first convert this into an equation. First convert it to an equation. Then I'm going to take a look at that equation and see if I know how to graph it. That is a parabola that opens sideways, right? This is a parabola that opens sideways, so it should look like this. This is y squared equals x. Then what I do is I go back to the original inequality and I say, do I have a bar here? Do I? No. So that means I don't want that parabola to be part of my answer. So I'm going to make this a dashed parabola instead. Those points are not part of my domain, right? Those points are not part of my domain. And then I'm going to pick a test point. And I'm either going to be within that parabola or I'm going to be on the outside. I just need one test point. So I can't pick 0, 0, right? This time I can't pick 0, 0 because 0, 0 is on the parabola. So I could pick this one, any point you want, really. I heard what?
1, 0.
1, 0, yeah. Let's pick 1, 0. And all I'm doing is checking to see if that works. Does this work? So we plug that into the original function. I'm testing 1, 0. And if I do that, I get f of 1, 0 is 1 times natural log of 0 minus 1. Uh-oh, that's bad, right? I get a negative number in the natural log, and that is undefined, which means that nothing inside, on this side of this parabola, nothing over here should work, which means only things outside this parabola over here will work. So if I graph this surface, what I should see is a picture only on that region, right? Like above or below it. This answers part B, because I say, oh, determine the domain. I should have, if y'all want it precisely, I'll do it precisely. Domain of F is the set of all ordered pairs such that x, where is it? Oh, sorry, y minus x squared. Y squared minus x is greater than 0.
When we say the domain F, it means point Z, right?
That means, well, no, it means the things that can be plugged into F. F is a function, right? It returns the z, it'll always spit out your z value, right? It always spits out your z. But the domain, we're talking about things that go in to it. The inputs.
Domain of Z.
The domain of F, no, because F is the function. F takes a point
Makes Z.
and it turns it into Z. But not saying that Z is F. I'm saying F is a function. What can you plug into it? The domain of F. You don't say the domain of Z. You say domain of F. F is the name of the function.
So point can't have. Well, actually, but
The function is the thing that does the operation, right? The function is the thing that takes something in, spits something out. The domain of that function are the things you're allowed to plug in. The outputs are not, it's not the same as the function. The function is the operator. It's doing the operation. The output is the numerical value that comes out. I think what you're talking about is, this right here is the function's value at some point. That's the function's value at a point. The function itself, f, is the operator that does the actual computation.
you can see how I would think that the domain of that point Z would be the sum of the X and Y.
To talk about the domain of a point doesn't make sense because the domain of a point, what you could ask me is where did that point come from, right? What input over here gave you that output?
It comes from the domain.
That comes from the domain, but it's not the domain, right? A point can't have a domain. It can only have where it came from, one specific place it came from. If you want to look at all of those together, then you're talking about the domain of F. All right, y'all ready to look at this one?
Yes.
We are not going to do B. We're not going to do B part 2. All right. I am going to show you the graph. This one is a really cool graph. And let me cheat first. I want to look at it from the top first. So I'm going to be looking at it from infinity up in the sky, right? And when we look down at this thing, we should see this, right? We should see that. I don't know why it's doing this. It's weird. Gotta zoom in. There it is. Okay, that's what it looks like from the sky. And now what I'd like to do is move it so you can actually see what this shape looks like. So here we go. All right, that's the surface.
That's really
Again, it's jagged because the computer's like, shit, I don't know what to do. I'm getting really huge numbers, but there's our surface. So where are we headed in this class? Some of the things that we're going to do, and I don't want to get too far ahead of ourselves here. One thing would be, if this thing has like highest and lowest points on it, right? It'd be nice if we could find those peaks and valleys of this thing. Also, if we were to like just release a ball, put a ball on that and just let it go, like what direction is it going to go in, right? Things like that. That's where we're going. But first we need to understand the basic idea of what a function of two variables looks like, and continuity, limits, all that stuff. Yes?
What is this function doing at the edge of our domain?
It's asymptotically approaching negative infinity.
Is it doing that?
Yep. Yeah, this thing, imagine this just keeps on going down. It's like a waterfall, right? It's like this waterfall, and you're just going to go.
Gotcha.
Yeah.
I didn't remember my rules for limits on that.
Now we're not actually getting into like why it's going to negative infinity. I mean, you could start plugging in some values and start seeing what outputs come out, but we're not. We're waving our hands.
But I just couldn't remember them properly. That's all.
Okay, how about this one? How are we doing here? 20 minutes. Okay, so for this one, we have determine the domain and sketch it. So here I'm not asking you to plug points in because that's kind of trivial, don't you think? Just plugging numbers in. So what's a domain? Well, we need to make sure that what's underneath this root, right? That must be greater than or equal to 0 here, right? We got to make sure that what's underneath that radical remains positive or 0. We can take square root of 0. And boy, how do we solve this? Well, we could do the same thing. Do you want me to do the same thing I've been doing? Yeah, just make it an equation first. Making the equation first, all right? And then I'm going to move everything around because I recognize this is a circle. If I take my variables to the other side, this is a circle, isn't it? Circle of radius 3. That's a circle of radius 3. And so I know that I have this circle. Do I include the points on the circle? Well, I have my bar here, right? So I do want the points on the circle. I just need to figure out whether or not I'm going to pick inside the circle or outside the circle. So I could do a test point. How about 0, 0? Test that point, 0, 0. Where do I test it? The original, right? The original up here. If I plug in 0 and 0 here, is this true or not? True, right? So it's everything inside. Are you all catching on to the idea of how I'm solving these inequalities? Drawing the graph as if it were an inequality, and then I'm testing the point to see whether or not I'm like on one side or the other side of the curve. There is another way, this is another way I kind of like to look at this problem, is if I do not actually turn into an equation and just move these two over like that, I kind of think to myself, well, x squared plus y squared, that's a circle centered at the origin. And then if this was equals 9, I'd be a circle. I want basically that to always be smaller than, well, radius of 3. I'm trying to get smaller, right? Anything 3 or smaller. So it's everything inside the circle. Either way, I mean, this way you'll get it. That way is more, I guess, kind of thinking of it a little more abstractly. There's the graph. That's the graph of this. It's just a dome, right? It's just like a dome.
Said it was a sweet.
So it almost is. I'm glad you said it. I'm actually going to show you something now. I intended on showing this. Check this out. Look at the original equation, or original function. Didn't we say that this right here is just the z value? Okay, so if I replace the left side with z, and now I square both sides of the equation, I get z squared equals 9 minus x squared minus y squared. And if I move all my variables to the left side, I get x squared plus y squared plus z squared equals 9. And that's the equation of a sphere of radius 3, isn't it?
Yeah.
So why didn't my picture draw the whole sphere? Only the positive values, because if I gave you this, that would be the whole sphere. But if I tell you to solve for z here, imagine going backwards, right? Here to here. This step from here to here, what would you actually have to do? Plus or minus. You'd have to do plus or minus, right? The positive one would draw the top of the sphere, and the negative would draw the bottom. So when we were here, yeah, so when we're here, we're already only drawing the top half, right? So that's why our picture looked the way it did. All right, we have another one. Okay, this is a little bit weird, so pay attention. A little bit weird, not real weird. This idea can be extended, right? Right now, what we had was a function that took in x and y and spit out z, right? So we had a function that took in a point in two-dimensional space and spit out a point in one-dimensional space. And we needed 3 dimensions to do that. But there's nothing stopping us from defining a function that takes a point in 3-dimensional space and spits it out an answer, right? Nothing. The problem with it is that we can't visualize it because we need 4 dimensions to visualize it. You would have to give me the input x, y, z, take that, have the function do something to those numbers, and then spit an output. Where do I put that output? Where do I put it? Right? I'm out of dimensions. You see what I'm saying? So we can't visualize a function that goes from R3 into R, right? We can't visualize it. Yes?
Isn't the vector form of equations also technically working in 4 dimensions?
The vector form?
Yeah, where we have R of t equals...
Okay, so when we have R of t equals a 3-dimensional vector, right? 3-dimensional. What this function r is a function that goes from r, right? It takes an input t, and it spits out a three-dimensional vector, right? So it goes from r into r3. The reason we can visualize that is because all we're looking at is the output. All we're looking at is the vector, the vector, the vector, the vector, the vector, right? We're not looking at t. T doesn't appear in our space curve. T's not in there, right? T's this background time. That's why we can do it. This is different because now what I'm doing is I'm taking a point in three-dimensional space and I'm trying to figure out this function that sends it to a number. Now the best way to understand this is, let's say you have a sphere, okay, like the Earth, okay? It's not a perfect sphere, I understand. Okay, so let's say you have this sphere and you go to some point on the sphere, x, y, z. What if that function gave you the temperature at that point? Then we don't need to visualize that, right? It would just be the temperature at that point. If you change the x, y, z, now you're at a different point, you have a different temperature, right? So we could have a function, a temperature function, which takes in your x, y, z and returns to you your temperature, right? Or you could say anything that you could really think of. Is there?
You can like visualize it with colors, right? Like red and blue.
What do you mean?
Like if it's hot, it's going to be like red, and if it's cold, like negative.
Yeah, sure. Yeah, so that you could have, your x, y, z, plug it into a computer, measure the temperature. If it's 90 degrees, between 90 and 100, then turn it red. And then over here you get green or blue, right? So you could use some other sort of visual, right, to help you. Yes?
You won't have to work with vector functions within multivariables, right?
What do you mean?
Vector functions with multiple variables, like what we're doing right now. Like we're just doing functions.
Well, yes, no. We are going to do vector functions of multivariables. So we are going to do vector functions that take in t and let's say take in t and s, right? And then spit back some three-dimensional vector. So you have two inputs and one output. Do you remember a few sections ago we worked on the equation of a plane? And I said this is the equation of the plane, but not the vector equation of a plane. Remember me saying that? If you want to draw you draw a plane with a vector equation, you have to be able to have two inputs, t and s, and then you can draw the vector function. So we are going to do that, but we will not go past we are not going to go past going from, this would be R2, right, two inputs, into R3. We will not go past that. But math majors, anyone who's going to do anything meaningful in like, you know what I mean? Like not math majors, but anyone, engineers, computer science, I mean, generally speaking, we should be able to go from Rn into Rm. Like it really doesn't matter. Like, there is no restriction. We stay in 2 and 3 here because we can at least grasp the ideas. But the higher, you go in math, you need this to be general. And actually there is infinite dimensional space where you have a vector that actually has an infinite number of components to it. That is a thing. Okay, your question?
Yeah, so question on our vector equations, t is time effectively.
It can be if you want it to be.
It's a good way to visualize.
Yeah, it's a good way to think about it, yes.
Is there a good way to think about the second one?
It depends on what we're trying to do. I mean, when it comes to like thinking of drawing a plane, let's think of it that way, okay? I don't want to get too far ahead of ourselves here, but this we can do. If I'm telling you that I can draw a plane using this, if I'm telling you that, what you can look at is that if I just do that, I'm going to draw a vector function of one variable draws curves, doesn't it? Mm-hmm. Curves. So I'm basically going to draw like curves in one direction, and then cover that up, and I'm going to draw curves in another direction. What I'm going to get is the plane. Just let it happen. It's coming. It's not coming anytime soon. It's chapter 13. It's chapter 13. You're going to be exhausted. You're going to be tired of this class if you're not already. You know what I mean? It's going to come, and it's one of the most dreaded sections I have because I have about this much time to get you to grasp how to draw surfaces using vector functions of two variables like that. It's cool if you get it. It's super cool. Just hang tight. It's coming. Right now, we are not doing vector equations. We are still doing scalar equations. That's what we call this, a scalar equation, because it's taking in numbers, spitting out numbers. That's what scalar functions do. Sorry, I said equations. We're looking at scalar functions. Okay, so this just says, hey, we can have a function that takes in x, y, z and spits out a number. I don't know where the root is on that. Why did that root? That's supposed to be a square root. So look at this one right here. Do y'all see that I have a function, takes in x, y, z, takes in an x, a y, and a z, and spits out some value. If I tell you to plug in 1, 2, 0, you just replace that with 1, 2, and 0, and we get an answer, right? So that answer might be the temperature at that point, whatever you want it to be. What's the domain of this? And then sketch that domain in three-dimensional space. This is supposed to be square root. So if I look at the domain of this function, right, it's the set of all ordered triples, right, x, y, z, such that the 9 minus x squared minus y squared minus z squared must be greater than or equal to 0. Right? Because all of this is sitting underneath a root, right? So I can't have a negative number in there. So I need that all of that radicand be positive or 0. And if we look at this, this is an inequality. How do we solve that inequality so we can graph it? What have we been doing? Set it equal to 0 first, right? Figure out what that is, and then do a test point, and then shade, right? So if I take this and make this an equation, equal 0, right? And then move things around, it's a sphere with a radius of 3. So this is a sphere, it's three-dimensional, right? Do I want to include the actual boundary of the sphere? Yes, right? So it's the sphere. Now, is it everything inside or outside? So we pick a test point, right? Good test point in there is the point 0, 0, 0, right? Does that work? Yes. Plug it into the original inequality, it works. So it's the sphere and everything inside of it, which means it's a ball. So that's the language difference, right? A sphere is just the points on the edge. The ball, solid ball, is everything inside on the surface and everything inside. So if we wanted to sketch this domain, right, it would be this. Solid ball, right? Radius 3. Centered at the origin, right? It's centered at the origin. I think that's obvious, right? We cannot draw the surface, we cannot draw the function though, right? That's the big kind of like, yes, we can draw the domain, but see the domain is three-dimensional? Every domain we've had before this, the domain has been two-dimensional, right? Now our domain is three-dimensional. The function, the visualization of the function, I don't have it. I can't provide it to you. Sorry. So that's it. 1 through 12 in the homework. I want you to try to see if you can do the range. I mean, if you can't, don't worry about it. Use a computer. The range is just the outputs, the z values. Is that a question? I didn't hear it. And find.
So like you partial derivative of y, partial derivative of x, and you see where the limit features from
Hold on. We're done, yes? We're done? Y'all good? You know what to do? Homework for 10.8, homework for 11.1, right? Okay, we'll come back. We'll get into 11.2. 11.2 is going to be limits and continuity. And then we get into, finally, the derivatives. So we get to try and find the slopes of tangent lines and stuff. Okay, let me turn this off, Lewis, and then I'll